Welcome back to the online course on embedded system design, verification and test. So, in this part we are discussing about the temporal logic, and in last class we have seen about a particular logic called CTL, computational tree logic. We have discussed about the syntax and semantics of CTL. Now, we know or we have idea about the meaning of a CTL formula. Now, today we are going to see about the equivalence between CTL formulas. So, when we say that two CTL formulas are equivalent, now what is the notion of equivalence in terms of CTL formulas? Okay. Now, we know about the equivalent formulas, and if you look back into the propositional logic and predicate logic, we know when we say two formulas are equivalent. As a simple example, I am giving here that P implies Q, or if P then Q, this is equivalent to not of P or not of Q, not of P or Q. So, all of you know this particular equivalence. That means, what it says, if the truth values of if P then Q or P implies Q is true, then the truth values of not of P or Q is also true. If the truth values of P implies Q is false, then the truth values of not of P or Q is also false. So, that is why we said that the truth values are same in all possible scenario, all possible truth values of their components P and Q. So, that is why we said these are the equivalence formulas. Now, in predicate logic, what we have actually, apart from those particular logical connectives, we are having two quantifier. One is known as your for all and there exist. Okay. For all x, that means for all possible values of x, the predicate P x is true. Okay. And there exists some x for which the given predicate P x is true. Now, in this particular case, we are having a relationship between for all and there exist. So, this is what we said, that if for all x P x, and if the negation is true for this particular formula, then what basically we can say that there exists at least one x, one value of x for which P x is false. Okay. So, for all values P x is true, if I say negation, that means this is not true for all values of P x. What does it means? At least we are going to one values of x for which P x is not true. So, that is why there exists not of P x. So, these two formulas are equivalent. So, these are for all possible values of your equivalence for all possible values of x and the given predicate P x. So, this is called for not of for x, for all x P x is equivalent to not there exists some x not of P x. Now, what is the notion of equivalence in case of temporal logic formula? How do we define the truth values of a temporal logic formula? So, basically we are having a model M and we are having a temporal formula say phi, or say in particular we can say that we are talking about the CTL formulas phi. Now, the truth values of this CTL formula defines over the model M, and also truth values is defined in a particular state of this particular given model M, because phi or CTL is a state formula. Truth values is defined on a state of a given model. Now, if you look into it, then what we can say that the truth values of this formula may be true in some state. Say if formula phi is true in this particular state, say as 0, they are having several possible transition, and in other state that Si the formula is not true. Okay. So, this is the notion of truth values of a CTL formula or in general temporal logic formulas. So, in case of state formula, the formula may be true in some state and may be false in some other state of a given model. Now, when we say the two formulas phi and psi are equivalent in case of CTL formula. So, basic notion is we say that two CTL formulas phi and psi are said to be semantically equivalent if any state in any model. This is the important thing. So, you just see that any state in any model which satisfies one of them also satisfies the other. So, if I am considering any model M, okay. So, in a particular state, say phi is true and psi is also true. In that case, what we are going to say that if truth values are same for any given model or any state, if they are always true, whatever model you are going to consider, whatever state you are going to consider, if phi and psi are always true, then we are going to say that they are equivalent. On the other hand, if phi is false, then psi is also false, then also we are going to say that they are equivalent. So, the truth values must be same in any state of any model. Then we say that these two formulas are equivalent. Now, how we are going to look for the equivalence? You just see that in case of your predicate logic formulas, we are getting a relationship between for all and there exists. That means, if for all it is not true, then there exists something for which it is false. We know about this notion. If for all some predicate is not true, then at least we are going to some values of x for which P s is false. So, this is the way we are going to look into the equivalence in the predicate logics. So, in the similar notion, we are going to see what are the quantifier that we have. So, here we are having two part quantifier, one is your A is your universal part quantifier and E is your existential part quantifier. So, it says there exists a part or in all possible part. So, these are having there exist and for all, which is very much similar to your predicate logic. So, we must have a relationship between A and E. So, if it is not true in all parts, there exists some part where the given formula is false. This is one issue, I can look into it. Another two we are having, one is the temporal operator G, which means globally, and another one is F, which is in future or eventually. So, if you look into it exact notion, then G can be treated as a universal quantifier of states along a path. So, we are going to talk for all possible state in a given path. So, that is why I am saying it is a universal quantifier of states along this particular path. Similarly, F, future or eventually, it is going to talk about a particular path, the particular state in this particular path. So, it is an existential quantifier of states along a path. So, again you just see that we are having the notion of for all and there exists in case of your paths. Similarly, we are having a notion of all states or there exists a state along a particular path, and this is captured with the temporal operators G and F. Now, by considering these particular four parameters A, E and G, F, we are going to have some equivalence formulas. Now, we are going to see what are those equivalence basically we are going to have. So, first equivalent formula we are writing it as naught of A f phi is equivalent to E g naught of phi. Okay. What does it means? Naught of A f phi. It says that in all path in future phi is true is false. So, it says that in all path in future phi is true is basically false. That means, in all path in future phi is not true. So, since it is going to be false in all paths, what we can say that there exists a path where globally phi is not true. So, there exists a path where globally phi is not true. That means, you can say that if in a particular path, if phi is not true, then what will happen? At least in this particular path, phi is not true globally. So, at least in this particular part in future we are not going to get any state where phi is going to be true. So, that is why it says that in this particular part f of phi is not true basically, not true. And if it is going to happen in all the possible paths, then we are going to say that in all path in future phi is true is false basically. So, here this is equivalent to, now you can say that at least there exists a path where globally not of phi is true. Now, if you consider any model and if you go to any state of a particular in any model, then if the truth values of not of A f phi is true, then the truth values of E g not phi is also true. Similarly, if the truth values of not of A f phi is false, then truth values of E g not of phi is also false in that particular state. So, if you consider any models and you look for any particular state, you will find that if the truth values of both the formulas will be same, either both are true or both are false. So, that is why we are going to say that these two CTL formulas are equivalent. This is the first equivalent formula that we have observed. So, not of A f phi is equivalent to E g not of phi. Okay. Another one, now it is the reverse, you can now correlate. Second equivalent formula is not of E f phi is equivalent to A g not of phi. So, not of E f phi, what does it means? There is a part where in future phi is true is false, because this negation is there. So, we are talking about the formula E f phi and this is the negation. So, there is a part where in future phi is true is basically false. The exact meaning of this formula is telling like that. So, A g not of phi. Okay. What does it mean? In all part globally phi is not true. Okay. So, in all part globally phi is not true. So, again you just see, consider some scenario. If globally not of phi is true in a particular path, again the similar formula model I can have. Say this is your not of phi. So, in this case, in this path globally not of phi is true. Now, if you same scenario exists in all possible path, then we can say that in A g globally not of phi is true. So, if this is the scenario, now wherever you go, you are not going to get any path where in future phi will be true, because everywhere it is not of phi. So, this is also another equivalence that we have observed, not of E f phi is equivalent to A g not of phi. So, in any model in any state, if one is true, then other is also true. So, either both are true or both are false, and that is why we say that these two formulas are also equivalent. Now, we are talking about the relationship between path quantifier A e and the temporal operator f and g. Now, another temporal operator we are having x, which is your next step. Okay. Now, whether something is true in the next state, basically we are going to reason about it. Now, that next state is also having an relationship with all path and there exists a path. Okay. So, this is another equivalent that we are having, A not of A x phi is equivalent to E x not of phi. So, not of A x phi, basically what does it means or what is the exact interpretation? It can say that in all paths next state satisfies phi is false. So, what it says? In all path next state satisfy phi is false. Okay. So, this is the meaning. So, that means if I talk about one particular state and if I have some scenario something like that and say everywhere is not of phi, then what we are going to say that wherever you go, whatever path you are going to consider, in next state that satisfy phi is a false. That means, phi is not true in any of the next state. So, this is basically we said that there exists a path in next state not of phi is true. So, if you consider any path you will find that not of phi is true, and due to this region only what will happen, A x not phi is true. So, I can write another diagram. So, in this scenario also you see what is the status of the formula not of A x phi. You will find that not of A x phi is true over here, because in all part in next state phi is not true. So, at least one part we are having where not of phi is true. So, this not of A x phi is true in your this particular state S 0 not of A x phi, and this is happening because of this particular part. Okay. So, that means I can say that again S 0 models there exists a path x not of phi. So, again you see that we have got a relationship between the all path and there exists a path of this path quantifier along with the temporal operator next state. Okay. So, not of A x phi will be equivalent to there exists a path in the next state not of phi is true. So, these two formulas also have that same truth values in any state of any model, either both are true or both are false. So, that is why I said that these two formulas are also equivalent. So, this is the formula already I have explained. Now, here we can with the help of these three given equivalents we can get another three equivalents also, and you know about these things, a negation property. So, already you have seen that not of A x phi not of A f phi is equivalent to E g not of phi. So, if I negate both the side then they will also remain equivalent. So, after negating both the sides what I am going to get, A f phi is equivalent to not of E g not of phi. Okay. This is one equivalent, it is derived from this given equivalent, just taking the negation in both the sides. So, similarly, other two equivalents also come from these two equivalent. Not of E f phi is equivalent to A g not of phi. So, from here we can derive this particular equivalent by taking the negation in both the sides of the equivalence. So, E f phi will be equivalent to not of A g not of phi, and third one not of A x phi is equivalent to E x not of phi. So, given or by taking the negation, by negating in both the sides left hand side and right hand side, we are going to get A x phi will be equivalent to not of E x not of phi. So, now we are getting 6 basic equivalent relationship over here. Okay. Now, the way we have explained or we have seen how these two will be equivalent, you can draw some structure or model and just see how these two will be equivalent. In a simple way we can do it. So, these are the some equivalent formula that we have in our temporal logic or in particular CTL, computational tree logic. So, another equivalent or two equivalent here I am citing. One is talk about the future. So, A f phi is equivalent to A t until phi. Second equivalent E f phi is equivalent to there exists a path t until phi. That means, we are having temporal operator f. Okay. This temporal operator f is having some relationship with the until operator. This is the way we can say, and whatever it may be, if it is your A f or E f, then A f will be related to your A until and E f will be related to E until. So, this is the things. Now, what we are saying that A f phi is equivalent to in all part t until phi. Now, or E f phi is equivalent to E t until phi. Now, what is t? T is nothing but the truth value true. Here this coming as writing as t, but already we have introduced the notion of two symbols, one called top and bottom. Okay. While defining the syntax of our CTL formula, we have introduced these two notions, top and bottom, these two symbol, and basically top indicates truth value true and bottoms indicate truth value false. Okay. Now, while we are defining the semantics of CTL, we have defined the semantics in a given model M. Now, what we have observed of what the semantic has been defined for this particular truth values, it says that true is true in all state and false is false in all state. Okay. That means, true top or the truth value true will be considered as true in all state and bottom will be considered as false in all state. So, this is the two constant, we can say that two constant we are having in our CTL, which represent the truth values true and false, and the basic notion is like that true is true everywhere and false is false everywhere. So, that means, if I look into the now labeling of these things, that means, we can consider that everything is labeled with the truth value true. So, now in this particular case what happens? If I am having this scenario, then what will happen? Here I can say that in this particular state as 0, E f phi is true, at least there exists one part where in future phi is true. Now, by looking into the labeling, you say that true is true everywhere, that means, all the state this is true will be considered. So, that is why I can say that it can be written as a E true until phi, true will remains true until phi becomes true. So, this is the relationship that we are having. There exists a part in future phi which will be equivalent to there exists a part true until phi, and if some scenario prevails in all the part, okay, that in all part in future phi is true, then this can be again written as A true until phi. So, this is another relationship or equivalence relationship we have. The relationship is between future and until operator, and path quantifiers have to be same. If it is A, then A f phi is equal to A true until phi and E f phi is equivalent to E true until phi. So, by looking into it, what we are going to say that we are having total 8 CTL operator, because what will happen, we are having 4 temporal operator x, next state, globally, future and until. These 4 temporal operator will be preceded by path quantifier A and E in all path and there exists. So, altogether we are going to get 8 temporal operator in CTL, but out of this 8 temporal operator, we can say that 3 temporal operators are adequate to express the other operators. So, here we are going to consider one particular case. It says that AU, EU and EX form an adequate set of temporal operators for CTL, because we know that AX can be written in terms of EX, already we have seen, and AG, EG, AF and EF can be written in terms of AU and EU. Okay. Because you just see, already I have seen that AF we can express it as with until operator, true until F. So, basically AF phi can be written as your A true until phi. Again we have seen that relationship that AG and EFR is having a relationship. Okay. So, AG and EF are having a relationship, and similarly EG and AF is having another relationship. We have seen those equivalents. So, these 4 operators AG, EG, AF and EF can be either expressed with AU or EU. Okay. So, if we are having know the methods how to check the root values of this particular operator AU, EU and EX, then the root values of other operators can also be find out. So, that is why we are saying these are the adequate set of temporal operator. This is one particular set of temporal operator. We may have other adequate set of temporal operators. Now, you can correlate with these things. We are having three logic operator. One is a disjunction, conjunction and negation. We said that this set is also a complete set of operator for propositional logics, okay, or logic families, because any other operator can be expressed with the help of these three operators. Just today itself we have seen that P implies Q, okay. This can be written as your not of P or Q, okay. Just if you consider any operator that can be expressed with the help of or and not. So, we said this is the complete set of operator in case of propositional logic. So, similarly, here also we have observed that we can have a adequate set of temporal operators in case of CTL. With the help of those adequate set of operator, other operator can be expressed. We are considering or we are talking about 8 different operators we are having in CTL, but out of the 3 are adequate. One particular set of adequate set we are talking about AU, EU and EX. Okay. But this is not only the adequate set of operators, we can get some other adequate set of operators, but for that we need one more equivalent formula. So, this is the way I can say, already I have explained. So, if I am considering that this is the adequate set of operators, then what will happen? AXP is equal to not of EX not of P, that means it is expressed with this operator EX. AGP is equal to not of EF not of P, but it is not in that adequate set of operator. EGP also your not of A, F not of P. So, the G is expressed with F. Okay. The operator G is expressed with F. Again the operator F is expressed with U. Okay. That means finally, we are saying A until and E until. So, if you know how to check the root values of these 3 operators, eventually we will be knowing the root values of their corresponding operator also, because they can be eventually converted to this particular until operators. So, that is why I said that this is an adequate set of temporal operators. We are having one complicated equivalence over here. Just I will give the notion. It says that A phi until phi 1 until phi 2 is equivalent to, this is one big expression, but which involve until E. That means, we can say that A until can be expressed with E until. Okay. So, if A phi 1 until phi 2 is equivalent to not of the whole expression. So, what will happen? In not I am having 2 expression E g not of phi and E of not of phi 2 until not of phi 1 and not of phi 2, not of phi 1 and not of phi 2. Okay. So, this is the equivalence that we are having. Just I am going to give some notion how we are going to treat these things as equivalent. Now, you just see, if I consider this component E g not of phi 2. Now, just consider one part, then I can extend it to any part. Okay. So, E g not of phi 2, if all the states phi 2 is false, then we say that E g not of phi 2. So, at least in this particular part, we are not going to have A phi 1 until phi 2. though my phi 1 may be true in all the states, but phi 2 is not true. So, this is the component it says. So, if happens like that E is not of phi 2, then A phi 1 until phi 2 is false. Okay. Now, when it will become true? If I take the negation. So, that is why this negation sign is there inside this. Okay. So, if such type of scenario is happening and if I take the negation, then what will happen? At least A phi 1 until phi 2 is going to be true. It may be true, provided it is going to have the second component. Okay. Because now, here I am saying that phi 2 is false everywhere. Now, we consider another scenario what will happen. Say somewhere phi 2 is true at that particular point. Okay. If phi 2 is true at that particular point, then what will happen? Then this property is not holding over here. Okay. That means, in that particular case I cannot say that they will be equivalent. So, if such type of scenarios happens and if you say that in all the state phi 1 is true, okay, then phi 1 until phi 2 is true at that particular path. If it happens in all the these things, all paths, then A phi 1 until phi 2 will be true. So, in that case, now this is having a particular things. Now, say if all the places now my phi 2 is say false. Okay. But in some situation, if phi 2 becomes true, or say if phi 2 becomes true over here, then what will happen? A phi 1 until phi 2 is true, because the semantics you just see what we have defining. A phi 1 until phi 2 holds if for all paths S 1, S 2, S 3 like that, where S equal to S I, then phi 1 until phi 2 satisfied if there is some S I along the path such that M S I models phi 2, and for all j less than I we have M j equal to phi 1. Okay. So, now in this particular case I am talking about some S I, okay, and M S I model phi 2. Now, what is the scenario? If this S I equal to S 1, I am considering about this particular path, and if this S I become S 1, then what will happen? So, if S I become S 1 in that particular path, then we say that since phi 2 is true at that particular point, I am going to say that A phi 1 until phi 2 is true at that particular point. So, that means, if phi 2 is true over here itself, okay, then I can say that phi 1 until phi 2 is true at that particular point. So, what is the notion of times we are considering over here while defining the semantics? That means, future includes the present. I think in some previous lecture I have mentioned about future includes present and future excludes present. So, in this particular semantics, the way we are defining the semantics, what we are considering that future includes the present scenario also, present set. So, if phi 2 is true over here, then phi 1 until phi 2 is true at that particular point. So, that is why it says that not of phi 2 until not of phi 1 and not of phi 2, if there exists some sort of path, and then phi 1 until phi 2 may becomes true. Okay. A phi 1 until phi 2 may becomes true in that particular true. That is why we are putting this particular negation. Now, if none of these components are true, then we are saying that A phi until phi 2 will be true if the negation of this whole expression is true. Okay. So, this is the scenario that we are having. So, we are going to consider this is another equivalent, that means A until can be expressed with your E until. Okay. So, this is the basic this thing is negation of this whole expression. Now, we can apply the De Morgan's theorem, that means negation of this component and this component, negation of the other component. So, we are getting an equivalence relationship between A until and U until. Now, since A until can be expressed with E until or E until can be expressed with A until. So, we are going to get different set of adequate set of operators in case of CTL. So, that is why we can have now one adequate set like that. Here x we cannot avoid, because what will happen, A x can be expressed with E x, then until either we can take both until already we have said, or we are going to take one until, say if we are taking E p until q, then one of the operators I have to take from either Fusar or Global. So, you just we need one next state operator, we need one until operator, and we need any one of global operator or F operator. So, if I consider any of these three operators, then it is going to give me an adequate set of operators, because already I said that A x can be replaced with your E x, A f can be replaced with your E g. So, either A f or E g I am going to take, and A g is again replaced with the help of E f, and until A until can be expressed with the help of E until, okay, and E p can be replaced with your again until operator. So, this is the way you can find, and you can now construct different set which will be adequate to express all the CTL operator. So, these are some example of the adequate set of CTL operator. Now, if we know the method of finding the truth values of a CTL formula, say with the help of these three operators A f, E u and E x, then other operators can be derived with the help of these three operators. So, that is why we said this is the adequate set of operator. So, what we have seen, we are saying that we are having operator x, next state, global, f and until. Okay. We have seen that global and f is having one relationship. Global basically said in all states along that path, and if Fusar says there exists at least one state in Fusar along that particular path. So, we are having a relationship between E g, G and F along with the path quantifier A and E in all path, and there exists a path. Similarly, x is having a relationship for this all path, and there exists a path, and E is also having a relationship between A and E. That means, I am going to get a relationship between A x and E x, okay, and A u and E u, okay. But A g is having relationship with E f, and E g and A f is also having some equivalence relationship. So, with the help of these things, we are going to find some other equivalence between this operator, and with the help of these things, we can now find the equivalence CTL formula. The notion of equivalence can be looked from the meaning of those particular CTL operator. Okay. So, these are some other equivalence that we are having. So, what is this one? Basically, these are some sort of expressing the operator with the help of the same operator to get some sort of equivalence. So, you just see A g is representing with the help of A g only, E g is again representing with the help of E g. Similarly, A f, E f, A until and E until. So, this is A until and E until. So, now These equivalence basically give us the idea or the meaning of the given those particular CTL operator. Now, what it says first set, so I can now consider about this is one state, second set and third set. Now, what the first set says, AGP is equivalent to P and AX AGP, or EGP is equivalent to P and EX EGP. Now, you just consider something like that, say if so, it says that globally something has to be true. Okay. So, that means globally in every state of the model, wherever you go, this P must be true. That means, if I am going to consider in this particular state as 0, okay, it says that if P is true at that particular state, then we can consider, but this is not the only condition. We are having second condition also. What it says, in all part in next state, whatever is the next state we are having, they should also satisfy this particular AG5 property. This must also satisfy AG5 property. Okay. Now, it is a big model, so we are having lot of transition. Okay. Now, what will happen? We can talk about the truth values of this given formula, either AGP or EGP, in a particular state by looking into its the next state behavior. If next state, if we find that AG5 is true, okay, in all the next state, then we can say that AG5 is true in this particular given state also. Similarly, it holds for EGP also. In EGP, we will concentrate, look for any one of such type of path. If P is true over here and the next state also satisfies that EGP is true, there exists a path in next state EGP is true, then what will say? EGP is true in that particular state. Now, what basically it says, when I am going to talk about the global operator and I am looking for the truth values of this particular global operator in a particular state, then by looking into its next state, okay, we can find out the truth values of this particular global operator in a given state. So, that is why it is saying that AGP is equivalent to P, P must be true in that particular state, and in all part in the next state AGP must be true. Similarly, in all part next state EGP must be true if we are going to talk about EGP. So, that is why these are the two equivalents that we have in our CTL formula. Now, consider a second set. It says that AFP is equivalent to P or AX AFP, and similarly EFP is equivalent to P or EX EFP. Now, what it says? If P is true, then I can say that EFP is true over here, because in future I am going to get it, then EFP is true here, and finally, I can say that EFP is true here. Now, what it says? So, if I am going to look into it, then if there exists a path, so that EFP is true, then I can say that EFP is true over here. Okay. So, if I am looking into a particular state as 0, and if there exists a path in the next state EFP is true, then we can say that EFP is true in this particular state. So, this is the component that we are having. EFP is true in a particular state if there exists a path in next state EFP is true. So, if I can say that if P is true over here, in this particular state E f P is also true. Okay. So, like that E f P is equivalent to P or E x E f P. So, this component is clear to us. Now, what about the other component? If it says that if P is true here itself, then we are going to say that E f P is true. This is as per our defined semantics. How we are defining our semantics? How we are considering the time? We are saying that future includes the present. So, we are having a timeline. If this is the present, then here I am going to get past in this direction and here I am going to get future. So, when we are going to consider about the future behavior, it includes the present also. So, this is the way we are defining our semantics. Future includes the present. Okay. So, that is why if P is true here itself in a particular state S0, we will say that E f P also true here itself. Now, if we want to exclude present from the future behavior, then what will happen? We have to slightly modify our semantics, we have to redefine our semantics. It is possible, you try to look into it how you are going to define a semantics such that future exclude the present behavior. But in our discussion, the semantics is defined in that way that future includes the present behavior. So, due to that, this is coming over here P or E x E f P is equivalent to E f P. But if future exclude the present behavior, then what will happen? We can say that then in that particular case E f P will be equivalent to E x E f P. When we say these two are equivalents, if in our semantics we say that if future exclude present, then we may get such type of equivalence. But in our case, in our semantics, what we are considering future includes the present. So, that is why we are having these two semantics. Okay. And similarly, these are the last pair of equivalence where it is defining until in terms of next state. So, first we consider about this particular component. So, when I say about that P until Q, then P must remain true until Q becomes true. So, if this is the scenario, then what I am going to get? Here I am going to get P until Q is true, because P after that Q, P remains true, then after that I am going to get P until Q is true over here, P until Q is true here, and P until Q is true at that particular point. This is the scenario. Now, what it says? If P is true, and there exists a path in the next state E P until Q is true, then we are going to consider E P until Q will be true at that particular point. Okay. Now, this is the scenario. Similarly, if here I am going to say P and P until there exists a path in next state P until Q is true, then I am going to consider P until Q is true at that particular point. Okay. Now, what is this particular component Q? If P is true and there exists a path in next state P until Q is true, then we are going to say that P until Q is true at that particular point. Okay. So, similarly, we are going to say like that. Now, in next state whether P until Q is true or not, in this particular scenario, what is the status of P until Q? So, here now as per this definition, if Q is true in a particular state, we are going to say that P until Q is true over here. Why you are considering these things? Again, as per our defined semantics. And in the defined semantics, what is the notion of time? Present includes the future. Present includes future. So, that is why if q is true here itself, then I am going to say that p until q is true in this particular state. So, that is why this component is there. So, in this particular equivalence, what we are saying that E p until q will be equivalent to q if q is true in that particular state itself, or it must satisfy the other condition p must be true in that particular state and there exists a path in next state E p until q is true. Okay. So, similarly, for A also you can say that A p until q will be true in a particular state provided q is true in that particular state, or if q is not true, then we are going to look for the other combination, other part p must be true in that particular state and in all path in next state A p until q must be true. That means, now if you consider all path, if p is true over here and in all next state A p until q is true, then we say that A p until q is true over here. So, p must be true and we must have a scenario like that in all path in the next state A p until q is true. Okay. So, these are the equivalence that we are having. We can representing temporal operator with the help of its next state behavior. We are defining the temporal operator by itself, which is next state behavior, and these equivalents are going to help us to build a method to check whether a given CTL formula is true in a particular state or not. We are going to use this particular equivalence. These are the equivalents that we will be using to find out the truth values of a particular formula in a given state. Now, some of the pair of equivalence for pair of formulas I am just writing over here, EFP and EGP. EFP or EFQ and EFP and Q. So, these are the pairs of formula I am writing and we are just going to check whether these two formulas are equivalent or not, whether these two formulas are equivalent or not. So, what is the first one? EFP and EGP, there exists a path in future p holds and there exists a path globally p holds. Okay. Now, you consider any model, it is very simple actually, say p is true at that particular point. Okay. So, there exists at least one path where E f p is true, but in this particular model, in this particular state E g p is not true. We are not going to get any path where globally p is true. Say if I say that this is a not of p like that, but E f p is true. So, one is true, other is false. So, they are not equivalent. Now, similarly, now can you check whether AFP or AFQ and AFP or Q, you can check. So, basically what will happen, if they are equivalent, then you have to argue with the meaning of these operators. If they are not equivalent, then try to give a counter model where you can say that in one state, in a state one particular formula is true, other formula is false. Okay. Now, if I look into it, now I am just taking some subset. Okay. So, if I look into those particular subset, then what you are going to get? So, here I am writing some formulas, but I am picking up some smaller set over here. Basically, if you now try to look into those particular formula, you will find that these formulas are equivalent. Now, what I can say for the first one, so this is a formula, either p is true over here, then what will happen? There exists a path in future, at least we are going to get EFP is true or E F Q is true. Whether it is true or false, it is immaterial for us because one component is true. So, I am going to get that E F P is true at that particular point. Similarly, E F P or Q. So, since in this particular part somewhere P is true, that means in this state P or Q is true. So, E F P or Q will be true over here. Now, by looking into the notion or meaning of this particular operator OR and fusor, we can find that these two formulas are equivalent, where whatever model you are going to consider, if one is true in a particular state, then other will also be true. Similarly, you can look for the other one. So, other set we are going to consider over here, and here you will find that these are basically not equivalent. Already I have discussed or said that these two are not equivalent, because in fusor P may be true, but it may not be true in all the state of any part. Okay. So, they are not equivalent. So, one may be true, but other is false. But if EGP is true, then EFP will be also true. We do not have any problem about that. But if EFP is true, it does not guarantee that EGP is true. Now, what about the second formula? AFP and AFQ and AFP and Q, they are not equivalent. And to establish that not equivalent, what we can say? We can give a counter example over here. Now, I can talk about one counter example consisting of say 2 parts only. I am not going to consider more part. If this is the scenario, now what is the status of this particular formula? Now, what is the status of this formula? AFP and AFQ. So, if you consider this particular part, somewhere in fusor P is true, somewhere in fusor Q is true. So, AFP and AFQ is true in this particular part. Similarly, if you consider this particular part, AFP is true and AFQ is also true. Okay. So, if this is the scenario, then what will happen? I can say that AFP and AFQ is true in this particular state S 0. But what about the other component? AF, P and Q. So, here we do not have any state where both P and Q are true. Okay. That means AF, P and Q will be false. So, if I consider this particular state as 0 of this particular model, then one is true, second one is false. So, that is why I said that these two formulas are not equivalent. Similarly, now we can check for the equivalence of the other formulas also. So, consider this particular formula EFP and EFQ. Okay. Now, if I look into the formula, then what I will find that this is not a CTL formula. Why it is not a CTL formula? FQ and FP, they are not preceded by any part quantifier, but their conjunction is preceded by a part quantifier E. Okay. So, in that particular case, this is not a CTL formula, but in this particular case what will happen? If we have EFP and EFQ, it says that along any path, then either P must come before Q or other way around. So, either P may come first or Q may. So, basically in this particular case what will happen? I can say that P is true over here and Q is true over here, or it may happen that Q is true over here, P is true over here. So, there exists a path either FP is true and FQ is true. So, here also at least in this particular part we can say that this is true or maybe here also true. So, this formula now we have seen that there exists a path either P may come first before Q or Q may come before P. So, these things can be written as like that. There exists a path in fusor P and EFQ. P and EFQ, or there exists a path in fusor Q and EFP. So, if this is happens, then what I can say that there exists a part in which P, F P and F Q. So, though this is not an CTL formula, but this formula is equivalent to this particular formula, and if you look into the notion, you will find that this is a CTL formula. Okay. So, just I am showing one example, but it is not always possible to express this particular any formula to a CTL formula. So, this basically talk about the expressive power of my logic or CTL. So, what will happen? We are discussing about a CTL computational tree logic, but all cannot be expressed in CTL. So, it says about the expressive power of that particular logic. So, here we shown that these sort of formulas can be expressed with this particular formula, but all may not be possible. Like that, if I say that there exists a part in next state P holds, or there exists a part next to next P holds. So, this is also a formula, but you just try, but it will be difficult to express these things with the help of a CTL. It is not a CTL formula, because due to this part, this particular operator, temporal operator, it is not preceded by any part quantifier. Okay. But if I put another part quantifier, then the meaning will be different. Okay. So, it says along this particular part, but it may happen in different part also, but such type of formula cannot be expressed with our CTL. So, that is why expressive power basically says what are the properties that we can specify in our logic. So, we have discussed one logic called CTL, computational tree logic. Due to its expressive power, now researchers are looking for some other way to construct the formula, temporal formula, and for that we are getting different class of temporal logic formula. So, one here we are talking about CTL. So, like that people are considering about another way to do it, which is known as your LTL, computational tree logic, linear time temporal logic. Like that we have come up with some formula or logic called CTL star also. But in this course we are not going to discuss about it, just we are saying that we are having a varieties of temporal logic families, and the expressive powers are different for different families. Okay. So, with this I am going to end my lecture today. So, we will continue for other issues in the next class. Thank you.